We are finally beginning our chapter on differentiation, and it begins with the tangent line problem. So let's look at the function 3x minus x squared. If you're not sure where that lies, graph it. Okay, find the zeros, whatever you need to do. So what's happening at exactly x equals 1? Well, it's increasing, right? We'll say it's increasing, but how fast is it increasing? And at that point, we don't know. And what's the slope at that point? We're not sure, but it would probably be something close to this at that specific point. All right, so that's a tangent line because it's just touching one point. If we're talking about a secant line, which is what we're going to do, all right, we're going to find the slope of a secant line, and then it'll be very close to the slope of a tangent line. Okay, compute its slope. So slope is change in y over change in x. So change in y over change in x. So it ends up being over h. So actually, let me just erase that. There we go. So that's the slope of the secant line. To find the slope of the tangent line now, we could use this idea right here, except we're going to make h really, really small. Okay? So let's look at how to do that. So the slope of the tangent line, we're going to let h be really small. And we're going to do f of 1 plus h minus f of 1 all over 1 plus h minus 1. Change in y over change in x. All right, so we have 3 times 1 plus h minus 1 plus h, quantity squared, minus f of 1. You plug in 1, you get 3 minus 1, which is 2. All right, continuing on here. And remember, that's all over h. 3 plus 3h minus, I'm going to go ahead and distribute my negative and the parentheses here. So it's 1 minus 2h minus h squared minus 2. Again, all over h. Okay, if I simplify this, oops, 3 minus 1 minus 2, that's 0. 3h minus 2h, that gives me negative h squared plus h all over h. If I simplify this, take out an h, I get negative h plus 1 all over h. So I can write that as 1 minus h. So the slope of the tangent line is 1 minus h. But as h gets really close to 0, the slope is going to get really close to 1. And that's the idea of the tangent. And the basic idea of a derivative. All right, find the general formula. This time, instead of finding it at specifically 1, we're going to find it at any point. Okay, so f of x plus h, okay, any value x, minus f of x, all over x plus h minus x. So we have 3x plus h minus x plus h squared minus 3x minus x squared. All right, I'm going to do quite a bit of simplification for the sake of space. 3x plus 3h minus x squared minus 2xh minus h squared minus 3x plus x squared all over h. Okay. 3x's cancel. X squared cancels. It looks like everything has an h left over, so I'm going to factor that out. I have 3 minus 2x minus h left in the top. So remember, as h gets really small, okay, as h gets really small, the slope at any point would be 3 minus 2x. Okay, and that's one thing that we're going to do. We're going to connect the idea of a limit. We're going to let h get really small. Okay, So as we let h get really small, the slope then is equal to this at any point on our function f. All right, so the slope is changing. It's not a defined constant value. It's a variable value depending on what x value you're looking at. All right, and that is all explained here. This is called the derivative function, okay? We'd say f prime of x. All right, and this is the only way that we know how to do that. So we're going to connect all of our practice with limits with this idea of slope or the derivative and do a couple problems. So let's turn to the next page. All right, this is the fun part here. Part A, once we do that, it's going to make part B and part C and D very easy. Find the derivative for that function using the limit definition. So we have f prime of x. It's a good idea to set it up. Equals the limit as h approaches 0. All right, so I will write it out the first time. You may not want to do that for the sake of space. Okay, that's the limit definition of the derivative. Remember, that came from slope, and now we have a limit as h approaches 0. So we have 2 x plus h. Okay. This is the part that most people make a mistake on. Make sure you're subtracting the whole f of x function. Oh, come on. Okay, for some reason, there we go. All right. Okay, distribute it out, and remember you want to carry that limit as h approaches 0, so you don't forget about it. Once you get to this point, you should see that a lot of things cancel out. If they don't cancel out, then you probably did something wrong. Okay, we have 2x squared cancels out, 35 cancels out, 16x cancels out. Everything you see should be left with an h. Okay, so factor out that h. And take the limit. So as h goes to 0, you get 4x minus 16 for the slope. So that is the derivative function f prime of x. Now it's really easy to find the slope at different points. Okay, so for part B, f prime of -1, you just plug it into your function. All right, so 4 times -1 minus 16, we get -20. What can you say about the function at the point? Since the slope is negative, f of x is decreasing. All right, so I would like you in your whisk to do f prime of 0 and explain what the function is doing there, and also f prime of 6. Write it and include it in your whisk. Part C, we're going to combine a little bit more. We're going to find the equation of the tangent line at x equals 1. Remember, for the equation of a line, you need a slope and a point. So we have our slope. That's our slope. We're going to need our point, though. So what is f of -1? Well, if you plug it in, I think that you should get 53. I'm going to use, since I have a point and a slope, the point-slope method of finding a line. Y minus y1 equals m times x minus x1. Okay, if you want, you can distribute this out and write it in slope-intercept form, or you can just write it as an equation, 53 minus 20 times x plus 1. Oops, that's a 2. 1. Okay, you can leave it like that, or you can write it in slope-intercept, your choice. All right, and then the last thing that we want to do is how can you use the derivative to find the x-coordinate of the vertex? So this is a parabolic function. It's going to look something like this. the vertex is going to be located there where the slope is equal to 0. All right, so to find the x-coordinate of the vertex, we can just set our slope function for x minus 16 equal to 0. So we get 4x equals 16, x equals 4. There you go. So far we have a few uses of this, and we're going to get a lot more. This is just the beginning of derivatives. Don't forget to put that information in your WISC, and have a nice day.